Hi everyone, I'm Shen-Qing from Heinrich University, Düsseldorf. Today I'm going to talk about GenTUS, simulating user behavior and language in task-oriented dialogues with generative transformers. When you want to train a task-oriented dialogue system, you may need a user simulator. By interacting with this user simulator and retrieve some reward signals, you can update your dialogue system by reinforced learning. Commonly, we train them on the semantic level for efficiency. But you may find out there are some problems in this setting. The first change is the environment of training and deployment are different, which means you train your dialogue system with the user simulator on semantic level, but the real user will talk to your dialogue system in natural language. This difference may cause sub-optimized performance to your dialogue system. So training only on semantic actions will lack of language variation. So it is appealing to build a user simulator which is able to reply in natural language. How about directly adding an NLG module to your user policy? By this way, your model is able to generate response in natural language, but there are still some problems. First, we are not able to optimize the user policy and NLG jointly. Maybe one of them is rule-based, or it is not easy to backpropagate the gradient from two very different models. The second problem is the result of NLG sometimes is not natural enough in a given context. For example, when the system requests about the hotel area and the user responses inform hotel area north, then the NLG module may be able to transfer this semantic act to I want to find a hotel in the north. What about a different context? Like the system provide the wrong area information, inform hotel area south. Then the NLG module may not be able to transfer the same semantic act to no, I want one in the north, not south. So the question is, can the user model respond not only in semantic acts, but also in natural language? With semantic actions, it can make the user model explainable. It helps us to understand the user policy. With natural language response, it can increase the language variation and help the training scenario close to the real-world deployment. The second problem is how to adapt user model to a new domain or a new ontology. We know that rule-based user models are hard to adapt to a new domain because we need to redesign the rules, which requires a huge amount of expert knowledge. The second problem is the number of rules are getting intractable easily for complex domains. And sometimes data-driven user simulators are also difficult to adapt to a new domain because their feature representation are domain dependent, which means we need to redesign it to adapt to the new domain. And if you need to retrain the model, then this new data needs more annotations. So can the user model be domain independent and adapt to a new domain in a zero-shot fashion? The third problem is, can we configure the user simulator's behavior? We may train a neutral user from the corpus, and can we somehow reshape its behavior to get a more chatty one or a more incooperative user? To deal with these problems, we propose GenTUS, a generative transformer-based user simulator with encoder and decoder structure. The input of GenTUS has 4 parts. The first one is the system action. The system action are composed by a list of tuples, intent, domain, slot, and value. And the user history includes user actions from previous 3 turns. We also have the user goal, which is composed by a list of tuples, domain, type, slot, value, and status. The type describe this slot is an information slot or requestable slot. And the status records this slot has been fulfilled or is not mentioned, and so on. And we also have the turn information, the current turn number. The output of GenTUS has 2 parts. The first is the semantic user action and the utterance in natural language. Here we can find out the text generated by GenTUS is not only conditioned on the semantic action generated by itself, but also on the context information. In addition, we represent the input and output as JSON format string. So both of the input and output contain only words, which means we can train GenTUS as a sequence-to-sequence language model. We initialize our model by BART, which is a transformer-based natural language generator, and has a bidirectional encoder and a left-to-right decoder. But we all know that language generator models sometimes is not so reliable, such as suffering from hallucination response. So how to prevent GenTUS generating illegal semantic actions? For example, in wrong format, there should be only one intent instead of two, or on existing actions, like there is no address for a taxi. To deal with this problem, we add a constrained semantic decoding space. How to build this decoding space? First, we select all possible intents from the ontology, such as domain-specific intents like inform and request, or general intents like greeting and thanks. The possible domains, slots, and values are from the user goal. Here, I would like to highlight that we tag the ontology as an additional input, not part of the model, which means GenTUS is domain independent or ontology independent. It is able to adapt to an unseen corpus, unseen ontology in a zero-shot fashion. So how to generate the semantic action from this graph? The idea is instead of selecting tokens from the whole vocabulary size, GenTUS can only select intent, domain, slot, and value from this diagram. For example, from all possible intent list, it may select inform as its intent. And for all possible domain, it select hotel instead of taxi. And then it can only select slots from the hotel domain, for example, area, and the value belongs to the area slot. Then it can choose to keep generating semantic actions or stop. If it chooses terminate generating semantic actions, then it can generate natural language response based on given context information and the semantic action generated by itself. Then this diagram can also be updated by the system action. For example, if the system mentions something not existing in this diagram, like price cheap, then we can insert new nodes into this decoding space. To evaluate the performance of GenTUS, we conduct several experiments. The first part is the direct evaluation. We train GenTUS as a natural language generation model and test it in this way. We also conduct a zero-shot transfer experiment. The second part is indirect evaluation. We train dialogue systems with different user simulator by reinforcement learning. And then we use human evaluation to evaluate these different dialogue systems. The third part is we fine-tune GenTUS by reinforcement learning to show it is able to be configured. The supervised learning, we train GenTUS as a natural language generation model. So we given the semantic X and the context information, then the model should reply the natural language response. Here is our baseline. The first is the text written by human in the corpus. And we also compare with the template-based natural language generation. The third model is SigGPT, which is a data-driven natural language generator. It takes the semantic action as input and generates the natural language response. There are two different ways to generate natural language response by GenTUS. The first mode is we provide not only the context information, but also the golden semantic action from the corpus. And GenTUS should generate text based on this information. The second one is we only give the context information, and GenTUS should provide the semantic action and the natural language response. We train our model on the multi-voice data set, which is a human-to-human conversation, including 10,000 dialogues, have 5 intents and 7 domains. The first matrix is the slot error rate. It measures whether the generated utterance represents the given semantic action. So we evaluate exact matching of semantic actions in the generated sentence. The second one is BLUE score. It measures the similarity of generated utterance to a reference in the corpus. The third one is a diversity matrix called self-BLUE. So for all generated sentences, the self-BLUE average the BLUE score of each generated sentence, which takes the other generated sentences as reference. And we also conduct a human preference test. We give the users dialogue history in natural language and the semantic user act, and the utterance generated by SGPT or GenTUS based on this given information. The users should evaluate based on informativeness, which means the given utterance contains all the information specified in the semantic actions. So it is similar to the slot error rate. The second one is naturalness, means the given utterance is human-like or not. All scores is from 1 to 3. Here is the result. Let's take a look at the slot error rate and informativeness. We can find out GenTUS has a comparable result to SCGPT. But when GenTUS generates language based on the semantic action generated by itself, it has the lowest slot error rate, close to human, which means the language generated by GenTUS can represent the semantic actions well. Then we can look at the BLUE score and the naturalness. We can find out, including the context information, GenTUS can generate more human-like languages than SCGPT. However, the language diversity of GenTUS should be improved because like we did not include bin search or sampling in our decoding space, in our decoding process, because we want to train a dialogue system with GenTUS, which means there's a huge amount of interaction. So we want to keep the computation complexity as low as possible. Then for the zero-shot transfer experiment, we include another dataset, schema-guided dialogue dataset, which is a human-to-machine conversation, including 20,000 dialogues, have 11 intents and 20 domains, which means SGD dataset is more complex than multi-voice. So we train GenTUS on 2 different models. So we have 2 versions of GenTUS and test on the same dataset or different one. So we can find out GenTUS trained on SGD is able to get comparable F1 score and accuracy when testing on SGD or multi-voice, which means it is able to transfer from known to unknown ontology in a zero-shot fashion. And its BLUE score is high when training and testing on the same dataset, but it drops when transferred to another corpus, which is reasonable because of the different vocabulary and language styles. The second part of the indirect evaluation, the idea is a better user simulator should be able to train a better dialogue system. So we train dialogue system with different user simulator. The first user simulator is a rule-based one, agenda-based user simulator with template-based natural language generation. The second model is agenda-based user simulator with SCGPT. The third model is our proposed model, GenTUS. And the user simulator provides natural language and the dialogue system replying in semantic act, because we assume that user can fully understand the dialogue system. Then we conduct an interactive human trial to evaluate these different dialogue systems. The dialogue system generates utterance by template-based energy, and each system is evaluated by 300 dialogues. 155 users are involved, and this system are evaluated by success rate and overall rating. Here is the result. First, we can find out GenTUS the system trained with GenTUS outperforms the system trained with agenda-based user simulator with template-based natural language generation and agenda-based user simulator trained with SCGPT on success and overall rating, which means training dialogue systems with a jointly optimized user policy and natural language generator can reach a better performance. Second, there is no statistical significant difference between the system trained by agenda-based user simulator with template-based NLG or SGPT on success and overall rating, which means including a data-driven natural language generator module with rule-based user simulator is not sufficient to train an optimal dialogue system. The third part is we fine-tune GenTUS by reinforced learning. We train GenTUS with a rule-based dialogue system on semantic level. So we have different turn-level reward function. The first one, we try to shorter the user action. So we give a penalty if the user generates longer user actions. The second reward function is in other way. We give a high reward if the user action is longer. And we also have a dialogue level reward. Give a reward for success dialogue and penalty for a failed dialogue, which means the user should modify their behavior, but still try to reach their goal. Here is the result. First, we can find out the success rate of both user 1 and user 2 are slightly higher than the supervised model, which is not surprising because we have the dialogue level signal. Then we find out the user 1, which try to shorten its action, has a similar behavior to the supervised model. We think the reason is the paid user in the corpus do not want to talk more than is necessary. So there is no space to shorten the user action. But let's take a look at the user 2, which has a longer user action, has a higher average action length, which means we can reshape the user's behavior by different reward function. We have a different user model, but tricky one. So in conclusion, GenTUS is able to generate semantic actions and natural language, and it can transfer to a new ontology in a zero-shot fashion. Its behavior can be reshaped by reinforcement learning. And in future work, we would like to modify its language part by reinforcement learning and including more information like user sentiment or personality. Thanks for your listening and looking forward to your questions.
Very much for the very interesting talk. Any questions from the audience? Yeah.
Error rate is lower than
You mean why or? Okay, I know how you mean, like this part. Yeah. Yeah, because I think one reason is it get used to, like, because the semantic action is also conditioned on the context information. So if I force to put the golden semantic act to generate the user action, then the model may be confused because this kind of input is not seen in the corpus.
Hello, this is Simon from Toshiba. Yeah, thanks for the interesting talk. So your model produces both semantics and text, right?
Yeah.
Is there a particular purpose? Does the policy training require the semantics? Is that why you generate the semantics as well, or could you do without just generating text?
Okay. So as I mentioned, the first purpose to still generate semantic action is we can understand the user policy more. It is make the model more explainable. The second part is, like as we show here, the GenTUS golden part, we can force change the semantic actions to get a different natural language response. So if we generate both semantic action and natural language response, it can let us more freedom to control the user model.
Okay. And then, so how do you ensure consistency between the text, the generated text and the semantic?
Yeah, so that's the purpose we evaluate the slot error rate. So if
Right.
the model can generate natural language in a low slot error rate, which means the language part can represent the semantic part well.
So yeah, you include that in the training.
Yes. So during the training, we have different signals like the exactly match of the semantic actions in the generated one and the corpus, and we also evaluate the blue score of the language part and in the language part. Yeah.
There's a question here.
Hi, Mike White from Ohio State University. It's a very nice result in your human evaluation showing that you were able to outperform the rule-based user simulator baseline. I was wondering if you did any further analysis to try to characterize, qualitatively where you're seeing this better performance. Or do you have any examples of where you found that your user simulator was especially important to get that better performance?
Okay, so I think one main reason is the language generated by GenTUS is closer to the human evaluations language. We take a look at the result, find like the template-based way or SGPT is not what user would interact. It's not a language user would interact to our system. And the second part is we find out the agenda-based user simulator has a longer user action in comparison to GenTUS. And when interacting with real user, they also tend to use shorter language, but longer terms. So I think the reason why the system trained with GenTUS can has a better performance is the behavior, the user policy of GenTUS is closer to real user, and the language style is also close to the user use our model.
Okay, but I guess that connects to your future work that some users might be quite different than others. Some might be chattier. And
yes,
so.
But that is also a difficult part to do the human evaluation. Like we given the user goal, so the paid user, they should follow the user goal to interact with our system. And should we provide more personal information, like ask this paid user to talk longer or shorter or more impatient? That make the experiment setting like more challenging. That is still something we need to test.
Thank you.
Thanks. I'm afraid we don't have any more time left questions, so let's thank the speaker again.